Hello guys, I know I'm posting late, but today I'll just be doing the chemistry revision, like chemistry final revision, for course question documents, CQD. I'll be doing grid questions and top questions. I already wrote down the answers to each question because most of them are just understanding rather than solving. So yeah, it's just a matter of memorization and yeah. So first, what happens when a system reaches equilibrium? We have to know these two main factors. The rate of the forward and backward reactions are equal, and concentration of both sides of the reaction stays are constant. And you can't say are equal. Equal does not work. So it has to be constant. Okay, so question 3 won't be included. Question 5, consider the following equilibrium system. Now they stated here now it's just removal and addition of certain substances here. Now they said the removal of Fe3 plus. Now here there's nothing specific to know. They didn't give us exothermic, endothermic, they just told us removal of Fe3 plus. Now we should know when the concentration decreases here, what happens to counteract this. The equilibrium counteracts this by decreasing the pressure here, by like decreasing the concentration of this, and then this decrease is because from here the concentration of this moves back to the concentration of the reactants. So product goes to the reactants. So what happens? The removal of Fe3 plus, the equilibrium tries to restore this removal of Fe3 plus by shifting the equilibrium from right to left or from product to reactants. So it shifts to the left, and when it shifts to the left, it takes the concentration of the product. So think of it as just taking away or decreasing the concentration of the product, which is this. So it decreases and shifts to the left. Now addition of product. What happens when there's an addition of product? The equilibrium will again try to keep everything equal, if that makes sense. So when, for example, here it increases, then the equilibrium will try to make this also increase, and by trying to make this increase, what they'll do. Oh wait, I misread that. They only want to increase in the reactants, not in the products. I misread that. So what happens here? When they increase the reactants, the equilibrium will also try to increase in the products. So what will happen? Concentration inside the reactants will move to the products in order to keep concentrations constant. Sorry, not equal, but constant. And so then everything can stay stable. So here the product increases if this increases, and in turn that will cause, this will just cause this to increase. So increase, and it will shift to the right. By shifting to the right, it takes the concentration of the reactants and it moves it to the products. So yeah, that's it for this question. Moving on, here now they're talking about pressure here. Now we should know in pressure that if pressure increases, the concentration shifts to the side with the least number of gaseous moles. Here, for example, there's two gaseous moles in total. 1, 2. And over here there's 2. If there's two moles on both sides of gas, that means the equilibrium does not shift, and the amount of products is not affected. Okay, now on this one here, we have to check the number of gaseous moles on each side again. So over here, there's one gaseous mole here, there's one gaseous mole here. Again, you always have to check the state. Here's gas. So that means these are gaseous moles. And here's also 2. Now over here, 3 is greater than 2. And 3 moles, other way around. Yeah, but 3 is still greater than 2. Over here, there's 3 gaseous moles, while over here, there's 2 gaseous moles. And when pressure increases, as said here, what happens? The equilibrium shifts to the side with the least gaseous moles, which means it shifts to the right, or it shifts forward. It's better to say forward. And here, when it shifts forward, what happens? It goes from left to right, and when it shifts forward, it reaches the product, and the product's to H2O. What happens? It increases. Okay, sorry, let me get this one out of the way. Now, 2NH3, no, okay, there's again all gas here. There's 2 gaseous moles here, and there's 4 gaseous moles here. So again, 4 is greater than 2. We have a case here. Now this time the reactants has less gaseous moles than the products, and in this case the equilibrium then shifts to the left, so it goes from right to left, or it shifts backwards. And when it shifts backwards, it increases the concentration of the equilibrium, increases the concentration of the reactants, and for the equilibrium to do that, it takes the concentration from the products, and it takes the concentration of the products and brings it to the reactants, since it's a reversible reaction, so that's possible. Therefore, amount of products decreases since the equilibrium is taking from the products. Now here it's about temperature, and in the case of temperature, we should know that when temperature increases, the concentration moves in the direction of reaction of the endothermic reaction. How to say this? Let's look here. I'll show you an example here. For example, if the energy is getting released, or if the energy is in the products, what happens? This shows us that the forward reaction is an exothermic reaction, and the backward reaction is an endothermic reaction. Now, here they said the temperature increases, which means that it goes in the direction of endo, which means it goes from right to left. So that means products decreases while reactants increases. So now we can look here. Yes, it shifts to the left, and products decrease. Okay. Now over here, and it's the opposite with XO. In the case where it's XO, that's when temperature decreases. The equilibrium shifts to the direction of the exothermic reaction. So here, it shows here that it's an endothermic reaction, and when it's an endothermic reaction, it's in the reactant side. The energy is in the reactant side, and that means here that when temperature increases, the equilibrium shifts the concentration to the right side. It goes from left to right, or it goes through the endothermic direction of the reaction. So what happens here? The equilibrium, if shifts from left to right, or just shifts forward, you could put here backward or left, and here you can put forward. It's better to put what I put in red. And when it shifts forward, what happens here? The product increases this time, and the reactants decrease. So here, the product increase. Now, over here, it shows here this time that delta H, or enthalpy heat change, is equal to a negative number. When enthalpy change is less than 0, what happens is this shows that this is an exothermic reaction, which means that the forward reaction is exo and the backward reaction is endo. They said temperature increases, which means that it is going through the endothermic direction, which is going from right to left, and that means that if it's going from right to left, products decrease and reactants increase. So it's shifting to the left or backwards, and products decrease. And that's it for 7G, or the 7th grade question. Now, number 8, we should know that in the addition of a catalyst, the catalysts don't get consumed in the reaction. As said here, they add a catalyst, and in any case, it does not affect the concentration, since catalysts do not get consumed in the reaction. But they just want to know what happens to the concentration. Just say no effect in the exam. Next question here, inert gases. They said this time they added inert gases, and no matter what, increase in pressure or decrease in pressure, whatever, there will be no effect since inert gases are unreactive, as said here. Sorry. Now, I'll look for the top question. Okay, well, now in this question here, they gave us two graphs and they want us to figure out if these reactions match these two graphs. Now over here, in this graph here, it states that as pressure increases, the yield product does not change. So when the yield product does not change, this is normally an indication that the number of gaseous moles on both sides of the reaction are equal. So let's analyze each one. Here they're not equal. So here, since it's here, it's 4, and here it's 2, so here is wrong. And over here, 2 and 3, which means this is wrong. And C, 1, here there's no gaseous moles, and here there's only one gaseous mole, so it's wrong. They have to be equal on both sides. Here, however, there's 2 and 2 here. So this is correct, or a possibility. And here there's 0 gaseous moles here and 3 gaseous moles here, so this is wrong. Now, you might think it's already done here. Now, yes, I can literally stop here and just circle D and move on. However, if I'll explain why this is also correct. Now look here. You could skip this part and move on, but I'll be explaining since this might be a different case in the exam. In this graph here, it shows that when the temperature increases, the yielded product decreases. Now we should understand that when the temperature increases, the flow of the concentration, it goes through the endothermic direction. And here, to know if it's going to the endothermic direction, you have to understand here that the product here decreases and here increases. And when the reactants increase, that means it's going from right to left, which means that this is therefore endo. The backward reaction is endo. Products are decreasing and reactants are increasing, which indicates why products are, which here it shows here product is decreasing. So that means reactants must be increasing, and therefore that shows that the concentration is moving from right to left or endothermic direction, since the temperature is increasing. Now, if the backward reaction is endo, that already shows us that the forward reaction is exo. And that means here that enthalpy change is less than 0. So let's look at each one here. This could have been a possible one, since here it is less than 0. The enthalpy change is less than 0, indicating that the forward reaction is exothermic. Here, it shows that the forward reaction is the endothermic reaction, which is not the case here. Here, this is also wrong. Here, this is part D, where both cases are correct, which is why part D is also correct. And here is wrong because the enthalpy change here is positive. So that already 100% shows that D is the correct answer. Okay, now moving on. And I believe this is not the final question here. There's 2 more top questions. Now, here they have a reaction here. They first asked us, write a source of hydrogen for this industrial process. Now, we learned this in another topic on, I think it was Haber process. But here, I just wrote from methane reacting with steam. This is how you get hydrogen in the product, of course. But you don't have to delve deep into it. Just say hydrogen is obtained from methane reactant with steam. Okay, now here we want to complete the table here. So let's look here, the increasing pressure, decreasing temperature, and adding catalyst. Now let's see here, first let's look at the reaction here. They give us that the backward reaction is endothermic. When the backward reaction is endothermic, that means the forward reaction is exothermic. So here we write endo, and here we write exo. So this will help us for this question. However, in the cases of temperature, we have to focus on the number of gaseous moles on both sides of the reaction. Here, number of gaseous moles here is 3, and here is 1. When pressure increases, the equilibrium shifts to the side with the least gaseous moles, so the concentration of the product will increase. Or in other words, how does it increase? It shifts from left to right, and that's basically just forward. So effect on the forward rate of reaction, it increases. The effect on the equilibrium yield of CH3OH, it increases since it's going from left to right. So therefore CH3OH is increasing. Now we'll apply the temperature rules, like where when temperature increases, the concentration shifts in the endothermic direction and vice versa. So here the temperature decreases, and when it decreases, that means the direction of the concentration flow goes in the exothermic direction this time, since now the temperature is decreasing. So it happens, in this case, when it's going from right to left, the right side decreases or the product decreases, and the left side increases or the reactants increase. So here, wait a second. Sorry, wrong direction. I put the wrong direction here. It's the opposite side. Here this increases, here this decreases, and it shifts this direction. I mixed up. I forgot that endo is backward, not forward. So here it goes from left to right, not right to left. And therefore we can conclude here that when the temperature decreases, the rate of the forward reaction, since it's going from left to right, this is forward reaction, so it... Oh no, actually, no. In the case of decreasing temperature, what happens when temperature decreases? Kinetic energy decreases. And when kinetic energy decreases, that means it will take longer for the reaction to reach the activation energy. Activation energy is the energy required for the reaction to, start up. So therefore since it will take longer for the reaction to begin or to be processed, that means the rate of the forward reaction will decrease. And the effect on the equilibrium yield of the product, which is this, what happens is it increases. And adding a catalyst, it is another... Now, I know adding catalyst does not really get consumed into the reaction. What it does instead is speeds up the rate of the reaction on both sides of the reaction. And it's the same case on why increasing temperature increases rate of the forward reaction. But no, actually it's a different reason. When you add a catalyst, instead of reaching the activation energy faster, what it does, adding a catalyst actually decreases the activation energy, which is another way of making the rate of the reaction faster. So that means it increases the rate of the reaction while having no effect on the equilibrium yield of any side of the formula or the equation here, or reaction. So that's it for 15, and now we finally have 16. Now here, part A, we'll just not do this because repeating the same question. Okay, we can get a better look at this question here. They give us here this reaction. They tell us that this is an exothermic reaction, meaning that backward is endo and forward is exo. They didn't write the correct arrow. I think it's supposed to be like this, but for now we'll just live. No, we won't live by it. We'll write like this. The left is endo and right is exo. Now they said there's a gas syringe containing an equilibrium mixture of hydrogen, bromine, and hydrogen bromide gases was sealed and heated to 300 degrees Celsius. Okay, so in this case here, we know that the backward reaction is endo, forward reaction is exo. So now we'll add to part B. Now over here they said that the pressure increases. When they press the syringe, the pressure increases. And they state here that the color of the gaseous mixture turns darker brown. We'll get to that later. Now, part I and part B give a reason why the position of the equilibrium did not change. So let's look back at this reaction here. In this case here, there's two gaseous moles here and two gaseous moles here. And in this case, when both sides of the reaction have equal number of gaseous moles, the equilibrium doesn't necessarily shift anywhere. So we can say gas moles are equal on both sides of the reaction. Now, in double I, suggest why the gaseous mixture turned darker brown. even though the position of the equilibrium did not change. So this is another thing that we do not discuss now. But in the case where the gaseous moles on both sides of the reaction are equal, what happens is the concentration on both sides of the reaction also increases. So here we can say the concentration of the whole reaction increases, which is another way to put it, as I said. So now in part C, the temperature of the gas syringe was increased to 400 degrees Celsius. And when we know that when temperature increases, the equilibrium shifts to the endothermic side, meaning that it shifts to the left or the backward reaction. So let's go back here and see here, part I, what happened to the position of the equilibrium when now they're just saying what happened to the position of the equilibrium when temperature increases. So we said that the endo is left and exo is right, which means that when temperature increases, that means it will shift to the endothermic side, and that means the concentration of the products will increase while the concentration of the reactants will decrease. The concentration will be moving away from the product, is another way to put it. So we go back and we say that it shifts right to left, or just shifts backwards. Okay. Now, in part II of part C, what happened to the rate of the forward reaction and the rate of the backward reaction when the temperature of the gas was increased? Now, again, we can put this in terms of particles. When the temperature increases, the kinetic energy increases, and that means that in the reaction, the activation energy will be reached quicker, and that means that the reaction will occur quicker. Which means we can say here that the rate of the forward reaction increases and the rate of the backward reaction increases. So everything increases. And that is it for chapter 1. It is not that hard of a chapter. It's really not. And yeah, that's it. Hopefully this video helped you. I know I posted late, but I take this as my way of studying for now. Because, this kind of motivates me to study. I wouldn't study if I didn't make this video. So thank you for watching the full video, and I'll make a video on chapter 2. Thank you.